Welcome to our journey through Earth's dynamic and often misunderstood geological wonders. Today we'll explore a couple of prevalent geology myths, unraveling the truths behind them with captivating insights. Let's embark on this adventure to deepen our understanding of the planet we call home. Segment 1. The myth of Earth's molten interior. Is the ground beneath our feet just a thin crust over a sea of molten lava? Let's dig deeper. Contrary to popular belief, Earth's interior isn't a vast ocean of molten rock. While the outer core is indeed liquid, composed mainly of molten iron and nickel, the mantle, a massive layer between the crust and the core, is predominantly solid. However, under immense pressure and temperature, mantle rocks can flow very slowly, a process known as solid-state creep. This slow movement drives plate tectonics, leading to earthquakes and volcanic activity. Understanding this distinction clarifies how our planet's internal dynamics operate. Segment 2. Unraveling the true age of Earth. Could Earth be just a few thousand years old? The rocks tell a different story. Some misconceptions suggest Earth is only several thousand years old. However, geological evidence paints a much older picture. Radiometric dating techniques have determined that Earth is approximately 4.54 billion years old. One of the oldest known minerals, zircon crystals from Western Australia, has been dated to about 4.4 billion years, offering a glimpse into our planet's early history. These ancient timekeepers help scientists piece together Earth's formative years and the evolution of its crust. Segment 3. The misconception of rare earthquakes. Think earthquakes are rare? Think again, our planet is constantly trembling. It's a common belief that earthquakes are infrequent events. In reality, Earth experiences thousands of earthquakes daily, though many are too small to be felt. Major earthquakes, those above magnitude 7, occur more than once a month, while great earthquakes above magnitude 8 happen about once a year. This continuous seismic activity results from the movement of tectonic plates and the release of stress along faults. Recognizing the frequency of earthquakes underscores the importance of preparedness and understanding Earth's dynamic nature. Segment 4. Decoding the formation of mountains. Are mountains formed overnight? The truth is a tale of time and tectonics. Some envision mountain formation as a rapid, catastrophic event. In truth, most mountains are the result of slow but powerful processes like plate tectonics. When tectonic plates collide, the crust can crumple and fold, gradually pushing up mountain ranges over millions of years. For example, the Himalayas continue to rise as the Indian plate presses into the Eurasian plate. This ongoing process highlights the dynamic and ever-changing nature of Earth's surface. Segment 5. The reality of sea level changes. Is sea level constant across the globe? The answer might surprise you. Many assume that sea level is uniform worldwide. However, sea level varies due to factors like temperature, salinity, ocean currents, and gravitational differences. Additionally, sea levels have fluctuated significantly throughout Earth's history due to climatic changes, tectonic activity, and glacial cycles. Understanding these variations is crucial for studying coastal processes and assessing the impacts of climate change on sea level rise. Segment 6. The misunderstood nature of volcanoes. Are volcanoes merely destructive forces? Discover their creative side. Volcanoes are often perceived solely as agents of destruction, spewing lava and ash with devastating effects. However, they play a crucial role in Earth's formation and ecological balance. Volcanic eruptions have created over 80% of Earth's surface, forming islands and mountains. The minerals from volcanic ash enrich soils, fostering lush vegetation. Moreover, geothermal energy harnessed from volcanic areas provides a sustainable power source. Thus, volcanoes are not just harbingers of destruction but also architects of our planet's diverse landscapes. Segment 7. The truth about Earth's shape. Is Earth a perfect sphere? The answer might surprise you. While many visualize Earth as a perfect sphere, it's actually an oblate spheroid, slightly flattened at the poles and bulging at the equator due to its rotation. This shape affects various phenomena, including gravity's variation across the planet. Understanding Earth's true form is essential for accurate navigation, satellite deployment, and comprehending global ocean currents. Segment 8. Unveiling the Age of Rocks. Can rocks be older than Earth itself? Let's investigate. It's commonly believed that all rocks formed after Earth's creation. However, some minerals, like zircon crystals from Western Australia, have been dated to about 4.4 billion years, offering a glimpse into our planet's early history. These ancient minerals provide insights into the conditions of early Earth and the formation of the continental crust. Segment 9. The dynamic nature of continents. Are continents fixed in place? Prepare to rethink Earth's surface. Contrary to the notion of static continents, Earth's landmasses are in constant motion due to plate tectonics. This movement has led to the formation and breakup of supercontinents over geological time. For instance, the supercontinent Pangaea existed around 335 million years ago before fragmenting into the continents we recognize today. This ongoing process influences seismic activity, mountain building, and the distribution of organisms across the globe. Segment 10. The reality of Earth's interior. Is Earth's core a fiery inferno? The truth lies deeper. While Earth's inner core is extremely hot, with temperatures comparable to the Sun's surface, it's solid due to immense pressure. Surrounding it is the liquid outer core, whose flow generates Earth's magnetic field. The mantle, though solid, exhibits plasticity, allowing slow movement over geological timescales. This internal structure drives plate tectonics, volcanic activity, and contributes to the planet's habitability. Segment 11. The misconception about fossil fuels. Are fossil fuels derived from dinosaurs? Let's uncover the source. A common myth is that fossil fuels originate from dinosaurs. In reality, they primarily formed from ancient marine microorganisms like plankton and algae. Over millions of years, these organisms were buried under sediment, subjected to heat and pressure, and transformed into oil and natural gas. Coal, another fossil fuel, originated from ancient plant material in swampy forests. Understanding this process highlights the extensive timescales required for fossil fuel formation and underscores the importance of sustainable energy sources. Segment 12. The surprising stability of Earth's magnetic field. Is Earth's magnetic field constant? Discover its wandering nature. Earth's magnetic field is not static. It experiences gradual shifts and occasional reversals. The magnetic North Pole, for instance, has been drifting northwestward over time. These changes are attributed to the dynamic movements of molten iron within the outer core. Studying the magnetic field's behavior helps scientists understand plate tectonics, navigate accurately, and even assess radiation exposure risks from solar activity. Segment 13. The formation of unique rock structures. How do nature's stone sculptures form? Unveiling the artistry of erosion. Natural rock formations such as mushroom rocks result from differential erosion and weathering processes. In arid regions, wind-blown sand abrades rock surfaces, eroding softer layers more rapidly than harder ones, leading to unique shapes. These formations provide insights into past environmental conditions and the relentless forces shaping Earth's surface. Segment 14. The misunderstood ice ages. Was there only one ice age? The past tells a different story. Many believe in a singular ice age, but Earth has experienced at least 5 major glaciations. The most severe, known as Snowball Earth, occurred over 600 million years ago, potentially covering the planet entirely in ice. These glacial periods have profoundly influenced Earth's climate, sea levels, and the evolution of life. Studying them helps scientists predict future climatic shifts and understand the resilience of ecosystems. Segment 15. The Origins of Precious Gemstones. Are diamonds the rarest gems? Unveiling the true treasures. While diamonds are highly valued, gemstones like rubies, sapphires, and emeralds are rarer. These gems form under specific conditions of temperature and pressure, often requiring unique geological settings. For example, rubies and sapphires are both forms of corundum, with trace elements imparting their distinct colors. Understanding their formation reveals the intricate processes occurring within Earth's crust and the geological history of their source regions. Segment 16. The Reality of Earth's Magnetic Field Reversals. Is Earth's magnetic field constant? Discover its dynamic nature. Many assume Earth's magnetic field is a stable, unchanging force, providing a consistent north-south orientation. However, geological records reveal a history of magnetic reversals, where the magnetic north and south poles swap places. These reversals have occurred irregularly over millions of years, with the most recent, the Bruns-Machiyama reversal, happening approximately 780,000 years ago. The evidence for these reversals is found in the orientation of magnetic minerals within ancient rocks. As molten rock cools, ferromagnetic minerals like magnetite align with the current magnetic field. Once solidified, these minerals lock in place, preserving a fossil of the Earth's magnetic orientation at that time. By studying sequences of volcanic and sedimentary rocks, scientists have constructed a timeline of these geomagnetic reversals, known as the geomagnetic polarity timescale. The cause of these reversals lies within Earth's core. The planet's magnetic field is generated by the geodynamo, a process driven by the convective movement of molten iron and nickel in the outer core. This movement creates electric currents, which in turn produce magnetic fields. Over time, the complex and turbulent flow within the core can lead to a weakening of the existing magnetic field and the initiation of a new field in the opposite direction. Contrary to popular fears, magnetic reversals are not catastrophic events. The process unfolds over thousands to millions of years, allowing ample time for life to adapt. While a weakening magnetic field during a reversal could slightly increase solar radiation exposure, there is no evidence linking past reversals to mass extinctions or significant ecological disruptions. Understanding magnetic reversals is crucial for various scientific fields. In geology, they serve as valuable markers for dating rocks and sediments, aiding in the reconstruction of Earth's history. In navigation and technology, knowledge of geomagnetic changes informs the calibration of compasses and the protection of satellites and power grids from solar storms. In summary, Earth's magnetic field is far from static. Its dynamic nature, evidenced by periodic reversals, reflects the ongoing vigorous processes occurring deep within our planet. Embracing this knowledge enhances our understanding of Earth's complex system and its ever-evolving character. Segment 17. The Misconception of Uniformitarianism. Do geological processes always occur gradually? Uncover the role of catastrophes. The principle of uniformitarianism, often summarized as "the present is the key to the past," suggests that the geological processes we observe today have operated consistently throughout Earth's history. While this concept has been foundational in geology, it's a misconception to believe that all geological changes occur gradually. Catastrophic events have also played a significant role in shaping our planet's landscape. Uniformitarianism, introduced by James Hutton in the 18th century and later popularized by Charles Lyell, challenged the earlier notion of catastrophism, which attributed Earth's features to sudden, short-lived events like floods and earthquakes. Hutton and Lyell argued that slow, continuous processes such as erosion, sedimentation, and plate tectonics could explain the geological record. However, modern geology recognizes that both gradual processes and catastrophic events are integral to Earth's history. For instance, the extinction of the dinosaurs approximately 66 million years ago is widely attributed to a massive asteroid impact, a sudden event with profound global consequences. Similarly, large-scale volcanic eruptions such as the Deccan Traps in India have caused rapid climate shifts and mass extinctions. Catastrophic events can leave distinct markers in the geological record. Impact craters, ash layers, and sudden shifts in fossil assemblages all point to rapid, significant changes. These events can reshape landscapes, alter ecosystems, and influence evolutionary trajectories in relatively short time frames. Understanding the interplay between gradual and catastrophic processes provides a more comprehensive view of Earth's dynamic history. It highlights the planet's resilience and the complex factors that have influenced its development over billions of years. In conclusion, while uniformitarianism emphasizes the importance of consistent processes over time, acknowledging the impact of catastrophic events offers a balanced perspective. Both gradual and sudden changes have sculpted the Earth, and appreciating their roles enriches our understanding of the planet's past and informs predictions about its future. Segment 18. The misconception of earthquake predictability. Can we predict earthquakes with certainty? Unraveling the myths and realities. Earthquakes have long been a source of fear and fascination, leading to numerous myths about their predictability. One prevalent misconception is that animals can sense impending earthquakes and exhibit unusual behavior as a warning sign. While anecdotal reports suggest that some animals act strangely before seismic events, scientific studies have not found consistent or reliable evidence to support this claim. The variability in animal behavior makes it an unreliable predictor of earthquakes. Another common myth is the belief in earthquake weather, suggesting that certain weather conditions can trigger earthquakes. This misconception likely arises from the human tendency to find patterns where none exist. Earthquakes originate from the movement of tectonic plates beneath Earth's surface and are not influenced by surface weather conditions. Studies have shown no correlation between weather patterns and seismic activity. The idea that earthquakes only occur in specific regions such as California is also misleading. While certain areas are more seismically active due to tectonic plate boundaries, earthquakes can and do occur in diverse locations worldwide. For instance, the 2011 earthquake in Virginia demonstrated that seismic events are not exclusive to traditionally recognized zones. This underscores the importance of preparedness, regardless of location. A particularly dangerous misconception is the belief that small earthquakes can prevent larger ones by releasing built-up energy. In reality, minor seismic events do not significantly impact the stress accumulation along fault lines responsible for major earthquakes. Relying on small quakes as a preventive measure can lead to a false sense of security. The notion of megaquakes, or earthquakes of magnitude 10 or higher, is another area of misunderstanding. The magnitude of an earthquake is related to the length of the fault on which it occurs. The longer the fault, the larger the earthquake. The San Andreas Fault, for example, is approximately 800 miles long. To generate an earthquake of magnitude 10.5 would require the rupture of a fault many times longer than the San Andreas, making such events implausible. Understanding the realities of earthquake predictability is crucial for effective preparedness and risk mitigation. While scientists can estimate the probability of seismic events in certain areas over time, precise predictions of when and where earthquakes will occur remain beyond our current capabilities. Emphasizing education and preparedness over reliance on myths is essential for minimizing the impact of these natural events. Segment 19. The truth about fossilization and what becomes fossils. Are all ancient creatures preserved as fossils? Discover the selective nature of fossilization. The fossil record serves as a window into Earth's distant past, yet it represents only a fraction of the organisms that once inhabited our planet. A common misconception is that all ancient creatures become fossils, but fossilization is a rare and selective process. For an organism to fossilize, several favorable conditions must align. Typically, the organism must possess hard parts such as bones, shells, or teeth, which are more resistant to decomposition. Soft-bodied organisms, lacking these durable structures, are less likely to fossilize and thus are underrepresented in the fossil record. Rapid burial after death is another critical factor. Environments where sediments accumulate quickly, such as river deltas, lake beds, or ocean floors, can cover and protect remains from scavengers and decay. Without swift burial, organic material is likely to decompose before fossilization can occur. Even when conditions are ideal, the process of fossilization is complex and requires specific chemical environments. Minerals and surrounding sediments must permeate the remains, gradually replacing organic tissues and forming a petrified replica of the original organism. Variations in sediment composition, pH levels, and groundwater chemistry can influence this process, making fossilization less likely in certain settings. The concept of taphonomy, the study of what happens to organisms after death until their discovery as fossils, highlights the biases inherent in the fossil record. Factors such as an organism's habitat, the presence of hard parts, and the geological activity of the region all influence the likelihood of fossil preservation. For example, marine organisms living in sediment-rich environments have a higher chance of being fossilized compared to terrestrial organisms in erosive landscapes. Misinterpretations can also arise from pseudofossils, natural formations that resemble fossils but are not of biological origin. Mineral deposits can create patterns that mimic the appearance of bones or plants, leading to potential confusion. Distinguishing true fossils from these lookalikes requires careful analysis and understanding of geological processes. Recognizing the selective nature of fossilization enriches our appreciation for the fossils we do find. Each fossil represents a unique set of circumstances that allowed it to withstand the ravages of time, offering invaluable insights into the history of life on Earth. Segment 20. The misconception of Earth's unchanging climate. Is Earth's climate naturally stable? Uncover the dynamic history of our planet's ever-evolving climate. A prevalent misconception is that Earth's climate has remained relatively constant over geological time, with current changes being purely natural fluctuations. In reality, Earth's climate has undergone significant transformations, driven by both natural processes and, more recently, human activities. Natural climate variability. Throughout Earth's 4.5 billion-year history, the planet has experienced numerous climate shifts. These include ice ages, where vast ice sheets covered significant portions of the continents, and warmer interglacial periods. Factors influencing these natural variations encompass volcanic activity, solar radiation fluctuations, and changes in Earth's orbit and axial tilt, known as Milankovitch cycles. Human influence on climate. In the past 2 centuries, human activities have significantly altered this balance. The Industrial Revolution marked a turning point, with the widespread burning of fossil fuels, coal, oil, and natural gas, leading to unprecedented increases in greenhouse gas concentrations. Deforestation and certain agricultural practices have further exacerbated this rise by reducing the planet's capacity to absorb CO2. Evidence of recent climate change. Scientific data indicates that Earth's average surface temperature has risen by approximately 1.5 degrees Celsius, 2.7 degrees Fahrenheit, above pre-industrial levels. This rapid warming correlates closely with the surge in greenhouse gas emissions from human activities. The year 2024 was recorded as the hottest year on record, underscoring the accelerating trend of global temperature rise. Segment 21. The Enigma of Sailing Stones. Imagine rocks gliding effortlessly across a desert floor, leaving mysterious trails behind, without any human or animal intervention. How is this possible? In the heart of California's Death Valley lies Racetrack Playa, a dry lakebed renowned for a geological mystery that has baffled scientists and visitors alike: the phenomenon of sailing stones. These rocks, some weighing up to 700 pounds, traverse the flat desert landscape, leaving visible tracks etched in the cracked mud. For decades, the mechanism behind their movement remained one of nature's most intriguing puzzles. The phenomenon. The sailing stones of Racetrack Playa have been observed to move distances of several hundred feet, carving trails that can stretch for dozens of meters. These tracks vary in direction and length, with some stones even making sharp turns or reversing course. Interestingly, stones positioned side by side often embark on divergent paths, adding to the enigma. The trails are typically shallow grooves, a few centimeters deep, suggesting a gentle movement rather than a forceful shove. Early hypotheses. Numerous theories have been proposed to explain this curious movement. Early hypotheses range from magnetic fields influencing iron-rich rocks to the subtle vibrations caused by earthquakes. Some speculated that wind alone, especially during intense storms, could push the stones across the slick mud surface. However, calculations showed that the wind speeds required to move the heaviest stones would need to be extraordinarily high, making this explanation less plausible. The ice rafting theory. A breakthrough came with the ice rafting hypothesis. Researchers suggested that during rare occasions when the playa floods and nighttime temperatures plummet, a thin layer of ice forms beneath and around the stones. As temperatures rise during the day, this ice begins to melt and break into large floating panels. Gentle breezes then propel these ice sheets and the embedded stones across the wet, slippery clay surface, leaving tracks as the ice drifts. This theory gained traction but lacked direct observational evidence. Direct observation and confirmation. In 2014, a team of researchers from the Scripps Institution of Oceanography provided the first direct evidence supporting the ice rafting theory. They installed time-lapse cameras and GPS devices on select stones to monitor their movement. During a winter when the playa experienced flooding and freezing conditions, the cameras captured the formation of thin ice sheets. As these ice panels broke apart under the sun, light winds pushed them, along with the embedded stones, across the playa at speeds of up to 5 meters per minute. This movement occurred under very specific conditions: a flooded playa, freezing nighttime temperatures, sunny days to break the ice, and just the right amount of wind. Implications and significance. The confirmation of the ice rafting mechanism not only solved a long-standing geological mystery but also highlighted the intricate interplay of climatic and environmental factors required for such phenomena. It underscores the importance of patience and persistence in scientific inquiry, as well as the value of modern technology in unraveling natural enigmas. Moreover, it serves as a reminder of the dynamic and ever-changing nature of Earth's surface, where even seemingly inert objects like rocks can embark on slow, mesmerizing journeys under the right conditions. Segment 22. The Spectacle of Hydrothermal Explosions. Beneath the serene landscapes of Yellowstone National Park lies a hidden danger: explosive events that can reshape the terrain in an instant. What triggers these sudden hydrothermal blasts? Yellowstone National Park is celebrated for its geothermal wonders, including geysers, hot springs, and fumaroles. However, lurking beneath this picturesque surface is a less-known but equally formidable phenomenon: hydrothermal explosions. These violent events occur when superheated water trapped beneath the Earth's crust rapidly converts to steam, leading to explosive eruptions that can hurl rocks, mud, and boiling water over vast distances. Understanding hydrothermal systems. At the heart of Yellowstone's geothermal activity is a vast magma chamber that heats the surrounding rock. Surface water from rain and snow percolates down through cracks and porous rocks, approaching this heat source. As the water heats under pressure, it becomes superheated, remaining in liquid form despite temperatures well above the standard boiling point. If this pressurized water finds a pathway to the surface, it can result in the familiar eruptions of geysers. However, if the water is suddenly depressurized due to a structural failure in the confining rocks, it can flash into steam almost instantaneously, causing a hydrothermal explosion. Historical instances in Yellowstone. Yellowstone's geological record is punctuated with evidence of past hydrothermal explosions. One of the most significant occurred approximately 13,800 years ago near the northern edge of Yellowstone Lake, creating what is now known as the Mary Bay Crater. This event excavated a crater over a mile wide, dispersing debris across the landscape. More recent, albeit smaller, explosions have been documented as well. For instance, in 1989, Porkchop Geyser in the Norris Geyser Basin experienced a hydrothermal explosion that ejected rocks and created a new vent. Such events, while infrequent, highlight the volatile nature of the park's geothermal areas. Triggers and precursors. Several factors can trigger hydrothermal explosions. Seismic activity such as earthquakes can fracture confining rocks, leading to sudden depressurization of superheated water. Rapid changes in hydrostatic pressure, possibly due to the sudden draining of a hydrothermal system or fluctuations in the water table, can also act as catalysts. While some explosions occur without clear warning signs, others are preceded by increased geothermal activity, such as changes in geyser eruption patterns or the appearance of new hot springs. Monitoring these indicators is crucial for assessing potential risks. Safety and monitoring efforts. Given the potential hazards, Yellowstone National Park has implemented extensive monitoring systems. The Yellowstone Volcano Observatory, YVO, employs a network of seismographs, ground deformation sensors, and temperature monitors to detect changes in geothermal activity. Segment 23, The Enigmatic Menominee Crack. Imagine waking up to find a massive fissure has mysteriously appeared overnight in your backyard. What could cause such a sudden and dramatic shift in the Earth's surface? In October 2010, residents near Menominee, Michigan, were startled to discover a massive crack running through a forested area. This geological anomaly, now known as the Menominee Crack, stretches approximately 361 feet in length, measures over half a meter wide in certain sections, and reaches depths of up to 1.7 meters. Its sudden appearance and unique characteristics have intrigued both locals and geologists, prompting investigations into its origin and formation. Discovery and initial observations. The Menominee Crack was first noticed on October 4, 2010, by property owner Tom Dvorak. He recounted hearing a loud noise reminiscent of a gunshot the previous evening but found nothing unusual at the time. The following day he stumbled upon the extensive fissure cutting through his land. The crack disrupted trees, with some tilted at odd angles, and the ground on one side appeared uplifted, creating a noticeable ridge. There were no immediate signs of seismic activity or other natural events that could easily explain the formation. Geological investigations. Intrigued by this phenomenon, a team of researchers from Michigan Technological University, led by geologist Joshua Richardson, conducted a detailed study of the site. Their findings, published in the Seismological Research Letters, describe the Menominee Crack as a pop-up feature, a type of geological formation where layers of bedrock are thrust upward, creating a ridge or bulge on the surface. Such features are typically associated with regions experiencing compressional stress, leading to the buckling of rock layers. Formation theories. The exact cause of the Menominee Crack remains a subject of debate. One prevailing theory suggests that the region's unique geological history played a role. The area sits atop ancient glacial deposits, and the weight of retreating glaciers thousands of years ago could have left residual stresses in the Earth's crust. Over time, these stresses might have accumulated, eventually releasing suddenly to create the observed pop-up structure. However, unlike typical pop-up features triggered by identifiable events such as earthquakes or human activities, the Menominee Crack lacks a clear catalyst, making it a unique case in geological studies. Significance and implications. The Menominee Crack offers valuable insights into the dynamic processes shaping the Earth's crust, even in regions not known for significant seismic activity. Studying such formations enhances our understanding of stress accumulation and release in the crust, which has broader implications for assessing geological hazards. Moreover, the crack serves as a natural laboratory for geologists to observe the immediate aftermath of such events, providing data that can inform models of crustal deformation. Segment 24. The mysterious Mayotte seismic event. What caused a seismic wave to ripple around the world, undetected by humans but recorded by instruments globally? On November 11, 2018, a peculiar seismic event emanated near the island of Mayotte, an overseas department of France located in the Indian Ocean. This event was remarkable not for its destructiveness, no one felt it, but for its unique seismic signature that puzzled scientists worldwide. The seismic waves propagated around the globe, recorded by monitoring stations from Africa to North America, yet their origin and nature sparked widespread curiosity and investigation. Characteristics of the seismic event. Unlike typical earthquakes, which generate a complex set of waves including primary P waves, secondary S waves, and surface waves, the Mayotte event was dominated by an unusual low-frequency signal resembling a clean sine wave. This monochromatic signal lacked the high-frequency components characteristic of tectonic earthquakes and lasted for over 20 minutes. The uniformity and duration of the waves were unprecedented, leading to various hypotheses about their source. Investigations and hypotheses. Initial speculations ranged from clandestine military activities to atmospheric disturbances. However, geological investigations soon focused on volcanic activity as a plausible explanation. Mayotte had experienced a series of small earthquakes since May 2018, suggesting magmatic movements beneath the Earth's crust. Researchers posited that the November event might be linked to the movement of magma deep underground, possibly involving the collapse of a magma chamber or the emplacement of magma into the crust. Discovery of a new submarine volcano. In May 2019, a significant breakthrough occurred when marine geophysical surveys revealed the presence of a newly formed submarine volcano approximately 50 kilometers east of Mayotte. This undersea edifice, rising about 800 meters from the ocean floor, had not existed prior to the 2018 seismic event. The discovery provided compelling evidence that the mysterious seismic waves were associated with magmatic processes leading to the birth of this new volcano. The intrusion of magma into the crust and its eventual eruption on the seafloor likely generated the unique seismic signals detected globally. Implications for volcanology and seismology. The Mayotte seismic event and the subsequent discovery of the submarine volcano have profound implications for our understanding of volcanic processes and seismic monitoring. It highlights the potential for large-scale magmatic events to occur with subtle surface expressions, emphasizing the need for comprehensive geophysical monitoring in volcanic regions. Additionally, the event underscores the importance of global seismic networks in detecting and analyzing atypical seismic phenomena, which can offer insights into previously unrecognized geological processes. Segment 25. The mysterious sailing stones of Death Valley. Imagine rocks gliding effortlessly across a desert floor, leaving mysterious trails behind, without any human or animal intervention. How is this possible? In the heart of California's Death Valley lies Racetrack Playa, a dry lakebed renowned for a geological mystery that has baffled scientists and visitors alike, the phenomenon of sailing stones. These rocks, some weighing up to 700 pounds, traverse the flat desert landscape, leaving visible tracks etched in the cracked mud. For decades, the mechanism behind their movement remained one of nature's most intriguing puzzles. The phenomenon. The sailing stones of racetrack playa have been observed to move distances of several hundred feet, carving trails that can stretch for dozens of meters. These tracks vary in direction and length, with some stones leaving multiple trails, suggesting they change paths during their movement. The stones' movements are slow, often occurring over several years, making direct observation challenging. The phenomenon has been documented since the early 1900s, yet the exact cause remained elusive. Early theories. Various hypotheses have been proposed over the years to explain the movement of these stones. Strong winds. Some researchers suggested that powerful gusts could push the stones across the playa. However, the weight of the stones seemed too great for even strong winds to move them. Ice flows. Another theory posited that thin sheets of ice, formed during cold nights, could float on the playa's surface and when pushed by light winds could carry the stones along. While plausible, this theory lacked direct observational evidence. Magnetic forces. A more speculative idea involved magnetic fields interacting with the stones, but this lacked scientific backing. Breakthrough observations. In 2013, a team of researchers led by geologist Ralph Lorenz set up a comprehensive study to observe the stones' movement. They installed GPS trackers on the stones and set up time-lapse cameras to monitor the playa. Their observations revealed that the stones moved when the playa was covered with a thin layer of water, which froze overnight into a thin sheet of ice. As the sun rose, the ice began to break up into large floating panels. Light winds then pushed these ice panels, and the stones were carried along with them, leaving trails in the mud. This phenomenon, known as ice shove, explained the movement of the stones without the need for strong winds or other external forces. Implications and significance. The discovery of the ice shove mechanism not only solved a long-standing geological mystery but also highlighted the dynamic nature of desert environments. It demonstrated how subtle interactions between weather conditions and the landscape could lead to significant geological features. This finding has implications for understanding other similar phenomena in arid regions worldwide. Segment 26. The misconception of Earth's solid core. Is Earth's core a molten mass of lava? Let's delve into the surprising truth beneath our feet. A common misconception is that Earth's core is a vast, molten sea of lava, akin to the fiery eruptions we witness on the surface. In reality, Earth's core is primarily composed of iron and nickel, with the inner core being solid and the outer core liquid. This distinction plays a crucial role in generating Earth's magnetic field and influencing geological processes. Structure of Earth's core. Earth's core consists of two distinct layers. Inner core. Despite temperatures comparable to the Sun's surface, the inner core remains solid due to immense pressure. It is primarily composed of iron and nickel alloys. Outer core. Surrounding the inner core, the outer core is liquid and also composed mainly of iron and nickel. The convective movements within this liquid layer are responsible for generating Earth's magnetic field through the dynamo effect. Generating Earth's magnetic field. The movement of molten iron and nickel in the outer core generates electric currents. These currents produce magnetic fields, and through the dynamo effect, these fields align to form a coherent magnetic field that extends from the Earth's interior into space. This magnetic field is vital for life, as it shields the planet from harmful solar radiation and cosmic rays. Implications for geology. Understanding the composition and behavior of Earth's core is essential for comprehending plate tectonics, volcanic activity, and the planet's overall geological dynamics. The heat from the core drives mantle convection, which in turn influences the movement of tectonic plates and the recycling of Earth's crust. Segment 27. The misconception of uniformitarianism. Do geological processes always occur gradually? Uncover the role of catastrophes in shaping our planet. Uniformitarianism posits that the Earth's features are the result of continuous and uniform processes. While gradual processes like erosion and sedimentation shape the landscape, catastrophic events such as volcanic eruptions, earthquakes, and asteroid impacts have also played significant roles in Earth's geological history. Gradual processes. Processes like erosion, sedimentation, and weathering have been instrumental in shaping Earth's surface over millions of years. These gradual changes have led to the formation of mountains, valleys, and sedimentary rock layers. Catastrophic events. Catastrophic events have also significantly influenced Earth's geology. Volcanic eruptions. Massive eruptions have created new landforms such as islands and plateaus, and have had global climatic effects. Earthquakes. Tectonic shifts during earthquakes can rapidly alter landscapes, creating faults and uplifting mountain ranges. Asteroid impacts. Large impacts have caused mass extinctions and have been pivotal in shaping Earth's biological and geological history. Implications for geology. Recognizing the role of catastrophic events alongside gradual processes provides a more comprehensive understanding of Earth's geological history. It highlights the dynamic and sometimes violent nature of our planet's evolution. Segment 28. The misconception of Earth's crust as a solid shell. Is Earth's crust a solid shell floating atop a molten interior? Let's uncover the surprising truth beneath our feet. A common misconception is that Earth's crust is a solid shell floating atop a molten interior, much like an eggshell encasing a liquid center. In reality, Earth's crust is a rigid outer layer that, along with the mantle, forms the lithosphere. This lithospheric layer is divided into tectonic plates that float atop the semi-fluid asthenosphere beneath them. Structure of Earth's interior. Earth's interior is composed of several layers. Crust. The outermost layer, varying in thickness from about 5 kilometers under the ocean's oceanic crust, to about 30 kilometers under the continent's continental crust. Mantle. Beneath the crust, extending to about 2,900 kilometers depth, composed of solid rock that behaves plastically over geological timescales. Outer core. A liquid layer composed mainly of iron and nickel, extending from about 2,900 kilometers to 5,100 kilometers depth. Inner core. A solid sphere composed mainly of iron and nickel, extending from about 5,100 kilometers to the center of the Earth at 6,371 kilometers depth. Tectonic plates and plate tectonics. The lithosphere, comprising the crust and the uppermost mantle, is divided into tectonic plates. These plates float atop the semi-fluid asthenosphere, a region of the upper mantle that behaves plastically over geological timescales. The movement of these tectonic plates is responsible for many geological phenomena, including the formation of mountains, earthquakes, and volcanic activity. Implications for geology. Understanding the true structure of Earth's interior is crucial for comprehending plate tectonics and the dynamic nature of our planet. The movement of tectonic plates shapes the Earth's surface, leading to the creation of continents, ocean basins, and various geological features. By dispelling these common geology myths, we've uncovered the fascinating and complex processes that shape our planet. Embracing accurate geological knowledge enriches our appreciation for Earth's dynamic history and its ever-evolving landscape. Stay curious and keep exploring the wonders beneath your feet.